This is Paris podcast number 76, and today we're doing the third part of this series, which is the aerodynamics of corrugated flapping wings in ground effect. And it's really cool. So if you haven't listened to podcast number 74 and 75, those are the first two parts of this series, and this third part will be today. And this is the final part. And we're going to be looking at this paper called Numerical Investigation on the Aerodynamic Efficiency of Bio-Inspired Corrugated and Cambered Airfoils in Ground Effect. So from the other podcasts, we know that we're looking at an NACA 4412 and a Dragonfly airfoil. And the reason why I really like Dragonfly airfoils is because they're effectively like, imagine getting a piece of paper and then just scrunching it up in one direction and then bringing it out. That's what a Dragonfly airfoil sort of looks like, generally speaking. And compared to a regular airfoil, which is usually thicker, a Dragonfly airfoil is really just like a very thin sheet. But the way that they produce lift is by flapping and putting them in ground, near the ground, you get a ground effect. So in the last podcast, we were looking at the drag coefficient and lift coefficient of the NACA 4412 and Dragonfly airfoils when they're one chord above the height of the ground and how that was affecting the these productions of lift and drag. Now we're going to continue and we pick up where we left off. So for both airfoils, the average drag coefficient and lift coefficients are shown in table 4, and they say that the aerodynamic coefficients do not change significantly when the mean ground clearance changes from 5 chords from the ground to 1 chord. As we mentioned in the last podcast, it's really the ground effect is very localized, so you need to get very close to the ground in order for a flapping wing to get any changes, good or bad. As we mentioned, sometimes the ground effect is not actually positive for a flapping wing, whereas with a stationary wing, let's say for a fixed wing aircraft, when you're in ground effect, it's almost always positive in terms of lift, whereas that's not always the case for a flapping wing or a different airfoil profile. But if the distance from the ground is equal to 1 chord, the aerodynamic coefficients are greatly affected and the ground effect is very apparent. So for the NACA 4412 and Dragonfly airfoils, the drag and lift coefficients are compared at 5 distances away from the ground, chords away from the ground, and 1 chord in figure 13. And by changing the distance from 5 chords to 1 chord, the values of the average drag coefficient across the entire flapping motion go from minus 0.073 to minus 0.12 and minus 0.057 to minus 0.07 for the NACA 4412 and Dragonfly airfoils respectively. So in other words, both airfoils, they see a dramatic reduction in drag, which means they get an increase in lift, in thrust, not lift. But interestingly, the drop that the NACA 4412 experiences is significantly greater than the Dragonfly airfoil. So they say the hysteresis loop of the drag coefficient is lower for the Dragonfly airfoil compared to the NACA 4412 airfoil at angles of attack less than 0 degrees. So the hysteresis loop is when you approach a certain condition from one direction, the resulting effect is not exactly the same as the other if you approach from a different direction. So in other words, if you increase angle of attack, you might get a lift coefficient of, let's say, 1.1. When you reduce the angle of attack to the same angle, though, but from the opposite direction, you might get a lift coefficient of 1. So it's a 10% difference, or a 9.19, whatever it is, 1919% difference. And they're saying here that for the Dragonfly airfoil below 0 degrees angle of attack, there's not actually much of a hysteresis loop compared to the NACA 4412, which indicates that the Dragonfly airfoil provides greater thrust than the NACA 4412 airfoil in this regime. However, when the angle of attack increases above 0 degrees, the drag coefficient hysteresis loop of the Dragonfly airfoil is higher than the NACA 4412. So in other words, it's very conditional. And I would also suggest that because it is so dependent on very small differences, that the accuracy of the research that we're doing now in Dragonfly airfoils is not accurate enough to actually predict this very well, because as we've seen, minor changes, such as just changing the angle of attack by a couple of degrees, significantly changes the trends. So moving on, the mean thrust coefficient of the NACA 4412 airfoil is 24.4% higher than that of the Dragonfly airfoil when they're both 5 chords away from the ground. But if you move these airfoils to only 1 chord away from the ground, the NACA 4412 mean thrust coefficient is 59% higher than the Dragonfly airfoil. So it seems like the NACA 4412 airfoil, when it's flapping, is significantly more affected by the ground effect than the Dragonfly airfoil. So is that a good thing for dragonflies or not, if this is that accurate, which considering that these changes are very big, major, I would imagine that these trends will hold in real life. And that is probably a good thing for dragonflies, because if you think that the dragonfly goes from being very close to the ground or the surface of the water or whatever, and then it goes up only even one chord, you don't want to get such a destabilization in the aerodynamic forces that you're producing. You want them to be stay fairly constant. Otherwise, you have to change a lot of other things. So by mitigating the ground effect, it might actually be beneficial for the dragonfly's flight. It can control itself much better and stay in control. It's sort of like what's better, going, I don't know, if you were to walk and then suddenly run, or while you're holding something, or just walking and then slowly accelerating to a run while you're holding something. Obviously, when you're holding something, you don't want it to fall out of your hand, so you want it to be a gradual change. That's kind of the same idea here. So when ground clearance alters from 5 chords away to 1 chord away from the ground, the average lift coefficient of the NACA 4412 airfoil and the Dragonfly airfoil augment from 0.339 to 0.4 and 0.08 to 0.095 respectively. So again, they both increase, but the NACA 4412 has a significantly greater increase, which again, I think it's because from a evolutionary point of view, you don't want yourself, like the dragonfly, to suddenly have a massive change in its aerodynamic forces, which could destabilize it as you just move it slightly away from the ground, because the ground effect is so sensitive and so delicate, the effects when with the distance. So the most effective ground clearance on the aerodynamic performance of both airfoils is 1 chord away from the ground, as it results in higher lift coefficients and lower drag coefficients than any other case. So let's look at the effects of the Strahl number. In the last podcast, I talked about the Strahl number briefly, and this just ties the flapping to a non-dimensional number. So the greater the Strahl number, the faster the object is flapping. So in this particular case, at least. So the impact of the Strahl number on aerodynamic coefficients of the NACA 4412 and Dragonfly airfoils at different angles of attack, they've done that. And based on these figures, it can be concluded that the increase in the Strahl number, so a greater flapping frequency, results in a decrease in the drag coefficient or augments thrust, and an increase in the lift coefficient for both wings. So for the Dragonfly airfoil, the average lift coefficient increases from 0.127 to 0.218 when the Strahl number goes from 0.26 to 0.6. So in other words, if you increase the Strahl number by a factor of 3, the average lift coefficient for the Dragonfly airfoil increases by about 40%. So it's not a linear increase, but it is a significant increase. The drag coefficient drops from 0.039 to minus 0.2, so a massive reduction. So in other words, making the wings flap faster for a dragonfly greatly affects the drag compared to the average lift coefficient. So as can be seen in figure 16, the lift and drag coefficients are compared at Strahl numbers of 0.2 and 0.6 for the NACA 4412 and Dragonfly airfoils. Let's look at figure 16. Let's go to that. There are quite a few figures in this paper, and they look pretty good. But figure 16 let me expand this window a little bit, show the drag coefficient for the different airfoils and the lift coefficients. Interestingly, if the Strahl number is very low, both airfoils don't have they have a fairly linear change in the drag and lift with angle of attack. But as you increase the Strahl number, both of them become very non-linear. So if you have a Strahl number of 0.2, let's say, both the Dragonfly and NACA 4412 airfoils have a very linear slope. So they're about, if you were to go from 0 degrees to 10 degrees, the drag coefficient goes from 0 to minus 0.02 maybe, or 0.5. It's not very much. And if you were to be at 5 degrees, it would be about half that. But if you were to put the Strahl number at 0.6, both airfoils at 0 degrees have a drag coefficient of 0 still, but at 10 degrees, they've now jumped up to about 0.5 or 0.6. Then at 5 degrees, it's only about 0.2. So it's massively non-linear. Why would that be? It's because as you're flapping, you're not only producing stronger vortices because you're flapping faster, but you also can utilize these vortices because these vortices are now still in the presence of the wing as you flap around. Whereas if you have a lower flapping frequency, if you flap and you produce a vortex, by the time you sweep back in that area, the vortex has already moved away because you've taken too long to get to it. So you can't really take advantage of the vortex. So what that means is these curves really indicate fairly linear lift and drag production, because that's what mimics our real life situation in general. In terms of how we produce lift as humans, we don't, well, traditionally we haven't looked at flapping wings. We've always had stationary wings or rotating wings, and they produce lift and drag very predictably. Whereas when you have flapping wings, you get these nonlinearities due to changes in flow physics, and you're actually you're using these vortices to your benefit. And I've gone on about this in quite a few other podcasts, in flapping podcasts, for example, podcast 14, 55, 56, and 57. I've gone on a lot about how flapping wings utilize vortices, and it's really cool. Let's move on here. The leading edge vortex starts moving towards the trailing edge vortex, towards the trailing edge, sorry, and separates from the airfoil. Simultaneously, as new leading edge vortices are generated, the flow is reattached, then lift force is recovered. So this shows how these vortices play a vital role in the flow over the wing. Therefore, this phenomenon will bring out many fluctuations in the lift plot. Again, why flapping faster will produce greater changes in the lift. When the airfoil continues downstroke and the airfoil and ground surface distance decrease, the low pressure zone surrounding the lower surface and of the airfoil moves to the trailing edge and becomes weaker. Hence, the leading edge vortex is intensified to some extent as the airfoil approaches the end of the downstroke at half the period of the stroke. So exactly a bit of an instant before the end of the downstroke. Consequently, the airfoil's upper surface pressure is greatly decreased, forming a suction zone, the source of the positive lift development. So that's how a ground effect can greatly increase the lift of a flapping wing. So you get an increase in the pressure underneath the wing and a drop in the pressure above the wing. So that's a twofold benefit. It's because wings, to produce lift, you need a pressure difference, and ideally a difference in pressure which is positive, so the lower pressure is on top, high pressure underneath. That will produce the lift force that you want. If you have the opposite, then that's downforce. So as a consequence of the ground effect, a greater pressure zone generated at the bottom surface of the airfoil acts like a trampoline. The leading edge vortex proceeds over the airfoil's upper surface and begins to disengage from the airfoil tail when the airfoil reverses its motion and direction. A low pressure zone is again produced below the leading edge vortex to produce leading edge vortices. Then the vortex interacts with the ground, slowing leading edge vortex separation and improving the lift force increase. The obvious difference between the two geometries introduced at a Reynolds number of 50,000 is the trapping of the airflow between the peaks and valleys of the pleated airfoil, so the dragonfly airfoil, and the creation of a very low velocity region, almost zero, which is the main benefit of bio airfoils over those of conventional airfoils. So in other words, these I've mentioned in other podcasts, in podcast number 74 and 75, how this corrugated wing can help roughen the surface, so it turbulates the flow, and it results in the badge layer becoming more turbulent. But here they're also saying, which makes sense, that having these corrugations, these peaks and valleys, it allows the wing to trap vortices more effectively, which means that you can take advantage of them to produce more lift and or thrust, which is really cool. Or in this case as well, potentially even mitigating the ground effect. So the next point in the figure of the speed contour, so just some figures that they had, is a lower speed gradient in the Dragonfly airfoil compared to the NACA 4412 airfoil, leading to the formation of the vortices on the leading edge and trailing edges with a greater distance from each other on the Dragonfly airfoil compared to the NACA 4412 airfoil. So in other words, just at these lower speeds, the vortices that are formed over the Dragonfly airfoil, the two main ones on the leading edge and trailing edge, they're further apart on the Dragonfly airfoil than the NACA 4412 airfoil. So they say this helps to increase the speed of the rotation of the airfoil of the Dragonfly one. So because these two vortices are further apart, so the airfoil can sweep back easier, they're saying. However, due to the high momentum and the high flow momentum and the thickness of the Dragonfly airfoil at 50,000 Reynolds number, the lift force of the Dragonfly airfoil is less than that of the cambered airfoil of the NACA 4412 airfoil. So that makes sense because Dragonfly airfoils are very thin, whereas NACA 4412s are fairly thick and they're already cambered. So they're going to naturally produce more lift when in most conditions. When you flap, though, under certain conditions, the Dragonfly airfoil will probably produce more lift and less drag, but also be more stable, as we've seen here. So the effect of the Reynolds number on aerodynamic performance. We've looked at the flapping frequency. Now let's look at the Reynolds number because obviously they fly at different speeds. So for the NACA 4412 and Dragonfly airfoils, the lift and drag coefficients are compared, the lift to drag coefficient ratio is compared at Reynolds numbers of 50,000 and 5,000. So at 50,000, the values of the lift to drag ratio decrease from 10.31 to 2.1 for the NACA 4412 airfoil, so a horrendous drop. But for the Dragonfly airfoil, it drops from 3.22 to 1.8. So to begin with, the lift to drag ratio of the NACA 4412 airfoil was a lot better. It was 3 times the amount for at around 50,000. When it drops to 5,000, now the Dragonfly airfoil and NACA 4412 airfoil lift to drag ratios are comparable, 2.1 compared to 1.8, with the Dragonfly airfoil being lower. And when the straw number, and this is also when you alter the straw number from 0.2 to 0.6. So the efficiency difference between the two airfoils at straw numbers of 0.2, 0.4, and 0.6 are approximately 211%, 64%, and 94%. So interestingly, it's not a linear decrease. It's there's a dip. So when the wings are flapping very slowly, the NACA 4412 has a efficiency of 211% greater, but then when it goes to medium flapping frequency, 64%, and then when it goes to faster flapping, then it's up to 94%. So there's this non-linearity. And this indicates that the lift to drag ratio difference decreases substantially with increasing frequency, but not monotonically. As a result, the lift to drag ratio of the NACA 4412 airfoil is better than that of the Dragonfly airfoil, especially at straw numbers of 0.2, so very slow flapping, which makes sense because Dragonflies do flap, whereas NACA 4412 airfoils were not designed for flapping flight. So for Reynolds numbers of 5,000, it was found that the Dragonfly airfoil had a better lift to drag ratio in all frequencies than the NACA 4412 airfoil, which is pretty wild because all we've done is drop the Reynolds number by a factor of 10, and now miraculously, the Dragonfly airfoil is far better in terms of its performance. They say actual numbers of 0.4, both airfoils exhibited maximal aerodynamic performance. So that's the juicy point, the optimum point. So now, this next part, they talk about figure 19. I'm going to go to figure 19 because there are a lot of cool graphs here. And I'm going to read to you it while we're looking at figure 19 so that you can keep an eye on it and it'll be more interesting for you. So we have figure 19 in view here. If you're just listening to this on YouTube, we do have the video, and also on Spotify, we also do have the video now as well. Take a look at the video as well if you want to see these graphs. So let's continue. In figure 19, the airfoil begins to rotate counterclockwise, and as the airfoil advances towards the ground, the low pressure zone formed underneath the airfoil starts to weaken. So in figure 19, you can see both the NACA 4412 and the Dragonfly one. The Dragonfly one is on the top, and you can see it's just like this little squiggle part, whereas the NACA 4412 has a much more conventional airfoil shape that we're familiar with. And as then come back up. So time equals T on 2, and 5T on 8 is where the Dragonfly, T on 2 alone is where it's closest to the ground. And going from left to right is where it is flapping down, and the second half, the bottom row, is where it's flapping back up. So accordingly, the vortex created at the ground surface is shrunk, and the separated vortices from the trailing edge move upwards as the low pressure area under the airfoil is weakened. At a time of T on T equals 5 on 8, so in other words, it's already flapped and now it's pulling back up. At the end of the downstroke, 2 low pressure zones are strengthened on the leading and trailing edges. As flapping proceeded, changing the clockwise rotation of the airfoil trailing edge, vortex separated. By moving away from the ground surface, a vortex is formed under the airfoil, and the high pressure zone on the upper surface airfoil is weakened. The cushioning effect results in a momentary rise in lift and drop in drag, induced by air compression between the airfoil and the surface below while flying near the ground or water. The rising pressure on the airfoil's bottom surface increases the lift coefficient. Along with the cushioning effect, the delayed stall mechanism created by a leading edge vortex that results in a low pressure zone on the airfoil's top surface. So let me explain this. This is really cool. We see it in a lot of dynamic wings. When you flap a wing, often you'll get something called a leading edge vortex. So at the leading edge, you get a vortex forming as you'd expect. Now, this vortex will often go, if you flap it properly, will often go over the suction surface. So it'll be just behind the leading edge. What this does is it creates this low pressure zone because vortices are low pressure cores. And this low pressure means that the flow gets sucked to the surface very well. And that means you can push it to high angles of attack while still keeping the flow attached because of that low pressure sucking the flow to it. And that's what they're talking about here. So a counterclockwise trailing edge vortex is also made close to the airfoil trailing edge. The increased lift coefficient found in the near ground situation is due to the leading edge combined with a cushioning effect. So the flow made by the airfoil produces shear layers at the ground. And this is quite interesting because I was actually talking with one of our amigos at Orlando Tillett about shear layers just the other day. So it's quite funny it's coming up now. And we'll talk about what this means. Actually, I should say now. A shear layer is just when you have two flows of different velocities, or just it could be different densities or whatever, of different parameters going past each other, and that creates something called a shear layer where one fluid is interacting with the other fluid, and then there's this like effect where effectively viscosity effect where they rip each other a little bit, and that's called a shear layer. And this is often it's often bad. For example, it can produce noise because you have two different velocities or two different densities or whatever interacting with each other. It's not uniform. But for this case, let's talk about it. So as the airfoil begins to pitch up, the leading edge and trailing edge vortices of the airfoil are shed, leading to a loss in lift. Sorry, this wording is a little bit tricky sometimes. At T on T equals half, so when it's completed the flapping down and it's close to the surface, the airfoil interacts with and destroys the ground shear layer. The lift coefficient becomes minimal due to the strong leading edge vortex generated beneath the airfoil and zero angles of attack. So because you're flapping down, the Dragonfly wing and the NACA 4412 wings have 0-degree angles of attack. And they say the airfoil begins its upstroke at T on T equals 5 on 8, and the lift gradually increases due to the caused velocity of the jet made by the shedding leading edge and trailing edge vortices. The leading edge vortex shed at the end of the downstroke collides with the ground, forming a new rebound vortex. The shift in the effective angle of attack of the airfoil caused by the flow due to the clockwise rebound vortex is a significant detection in the study. Whenever the airfoil is on its downstroke, the circulation of the rebound vortex to the surrounding fluid affects the angle of attack of the airfoil. Depending on the size and strength of the clockwise rebound vortex, the airfoil's vertical force can increase or decrease. So that's probably due to the flapping frequency and Reynolds number and distance away from the ground. So it shows just how dependent the ground effect is on all these different parameters. And trying to dampen these things would be a good thing. As illustrated in figure 20, so let's move to figure 20 now. We got some other cool figures. On the left, we have the NACA 4412 and Dragonfly airfoils on the downstroke. On the right is on the upstroke. And it's colored with the turbulent kinetic energy, which, as you'd expect, is the kinematic energy, in the turbulent regime. So the Dragonfly airfoil creates concentrated and strong vortices than the NACA 4412 airfoils due to its passive flow control. However, that's referring to the corrugated part, the crinkle cut bit. However, because of the high velocity of the far field flow, the trapped eddy in the corrugation cannot hold the vortices near the surface of the airfoil. As a result, a decrease in the Dragonfly-inspired airfoil performance is observed at high Reynolds numbers. I'm guessing that's also to do with the flapping frequency. If you were to push the flapping frequency higher, you should be able to capture those vortices. The main reason why I think that these vortices are not captured at high Reynolds numbers is because they move away too quickly for the airfoil to capture properly because the flow is moving faster. But if you were to flap faster, I think you'd be able to capture that a bit better. So as turbulent vortices rapidly separate from the Dragonfly airfoil surface, the ability to increase momentum and flow around the airfoil is lost, indicating the reason for significant fluctuations in the diagram of the aerodynamic coefficients of the Dragonfly airfoil. According to figure 20, this incredible two-dimensional complexity evolves in the boundary layer. Thus, this is the boundary layer that flows over the flat or smooth part of the NACA 4412 and Dragonfly airfoils. The developing and thickening of the bandrelay at the trailing edge and faster upper flow with slower lower flow created a von Karman street. That's really cool. They said as in figure 19. So this is where we're talking about having two different flows of different speeds, and then they interact with each other. There's this shearing effect, and this creates a von Karman street, which is really cool. You don't often, or sometimes you see it, but it's often associated with bluff bodies. Airfoils are not bluff bodies; they're streamlined bodies. So by having a von Karman street forming over this due to differences in velocity is really cool. So that was those figures and what I wanted to talk about. Let's move on to the next section now. So finally, in conclusion, the results indicated that a direct relationship between the lift-to-drag ratio of the airfoil and the ground effect occur, and at Reynolds numbers of 50,000, by increasing the straw number from 0.2 to 0.6, so increasing the flapping frequency, the values of the lift-to-drag ratio decrease from 10.34 to 2.1 and 3.22 to 1.8 for the NACA 4412 and Dragonfly airfoils respectively. This drop was dramatically more for the NACA 4412 than Dragonfly airfoils. So what does this mean? It means the Dragonfly airfoils are a bit less sensitive to changes in flapping frequency. They've dampened this negative effect. As a result, the lift-to-drag ratio of the NACA 4412 airfoil was better than that of the Dragonfly airfoil, especially at low oscillation frequencies. The results of the Reynolds number of 5,000 show that the Dragonfly airfoil had better lift-to-drag ratios in all frequencies compared to the NACA 4412 airfoil. So again, it depends on the regime that you're flying in. Finally, the NACA 4412 airfoil has a better lift coefficient than the Dragonfly airfoil at Reynolds numbers of 5,000 and 50,000. However, the aerodynamic performance of the Dragonfly airfoil is much better at Reynolds of 5,000 due to its low drag coefficient. So that's in this podcast. Make sure to like, subscribe, and if you're doing experiments like this or any other experiments, or you're doing CFD that needs experimental data to validate it, make sure you measure the density of the air that you're using. The reason why is because it changes from day to day, and even through the day. On average, on a regular day, this density will change by about 2 to 4%. That means that air is creeping through in the rest of your results, including the Reynolds number and the velocity of your wind tunnel and everything. So to overcome that, we make an instrument called the Atmosphere Hawk. It actually measures the density for you, and it gets rid of that error for you, and it has the values printed on a large screen for you, or so you can read it directly, or you can put it into your computer directly and factor that into your wind tunnel, and you can get rid of that error in real time. So when you get your data, you don't need to post-process it and get rid of the error. Podcast number 54, I go through how this affects your results and how it introduces error, both the forces and flow physics. Check that out. And the Atmosphere Hawk is linked in the description. Make sure to get one for yourself. And peace out, amigos.